Hello and welcome to section 1.3. Today we're going to talk about algebraic expressions. To start with the definition, a variable is a symbol that can represent a number from a set of numbers. So what we're talking about here is usually x or y. It's not necessarily x or y. Theoretically you can use anything you want. You could use a happy face if you wanted to as a variable. It doesn't really matter. Sometimes we'll get into Greek letters and use alpha and beta, but usually it's going to be x or y or z. An algebraic expression is a combination of variables such as x, y, and z, and some real numbers using addition, subtraction, multiplication, division, powers, and roots. Some examples of these will look like this. We might have, say, x squared minus 2x plus 4. Or maybe we have the square root of x minus 3. These are both examples of an algebraic expression. It doesn't have to be a polynomial, and we'll get into what a polynomial is in a second if you don't know what that is. Another algebraic expression is like this. 3y squared plus 4x over 3z. You can have multiple variables if you need. Usually, especially for this class, we're going to use either one or two variables, which will be x and y. A monomial, mono meaning one, is an expression of the form ax to the n, where a is a real number and n is an integer. A binomial, bi meaning two, is the sum of two monomials. As you can guess, a trinomial is the sum of three monomials. A polynomial is the sum of one or more monomials. Okay, let's get into a formal definition of what a polynomial is. A polynomial in the variable x is an expression of the form a sub n x to the n, all the way down to a sub 0, where a sub 0, a sub 1, a sub 2 are all real numbers, and n is a non-negative integer. If a sub n is non-zero, then the polynomial has degree n. The monomials a sub k x to the k are called the terms of the polynomial, and a sub k are called the coefficients. So what do I mean by this definition? Well, let's start with the terms first. A sub k, x sub k, what do each of these mean? Well, each of these are terms here for k equals 0 all the way up to n. So if k is equal to 0, then we have this term. If k is equal to 1, we have this term. If k is equal to 2, we would have the next term. And if k is equal to n, then we have this term. So each of these is called a term in this polynomial. Now, a sub k, the number in front of each x, is called a coefficient. A sub n is the coefficient on the nth degreed term. A sub n minus 1 is the coefficient on the n minus first degreed term, and so on, all the way down. Now, a sub 0 is just called the constant term. Notice that it isn't attached to an x. It sort of is, it's just that x is taken to the 0th power. And since x to the 0 is equal to 1, we just write it as 1 instead. If a sub n is not equal to 0, then the polynomial has degree n, means that if this coefficient is non-zero, then the exponent n is going to be the highest exponent in the polynomial. Now, whatever the highest exponent is, that's the degree that's what we call the degree of the polynomial itself. So here, n would be the highest exponent, so the polynomial has degree n. Okay, let's do an example here. Determine if an expression is a polynomial, then find the degree if it is a polynomial. A is 3x to the 4th minus 2x squared plus 1, and b is 2x to the 3 halves plus 3x minus x to the 1 half. So we need to determine if either of these are polynomials. Now, I want to note here, if we're looking at all of the things that could be algebraic expressions, we would have a set that looks like this. And the set would represent all of the algebraic expressions. Now, a polynomial is always an algebraic expression, but not all algebraic expressions are polynomials. So a subset of algebraic expressions is polynomials, right? So when we look at these, we need to determine which ones polynomials and which ones are not. This first case is definitely a polynomial. It fits the form a sub n x to the n plus a sub n minus 1 x to the n minus 1, and so on. Notice that we don't have an x cubed term. So in this case, if we write this polynomial out as we would have it in the definition, it would look like this. 3x to the fourth plus 0 x to the third minus 2x squared plus 0x plus 1. Something like this. Now, it doesn't matter if these are zeros or not. It just drops the terms so that the general case of a polynomial will fit all possible polynomials, right? So this is definitely a polynomial, and then we need to figure out what the degree is. Well, the degree is the exponent on the highest powered term with a non-zero coefficient. So the exponent here is 4. This is the highest powered term with a non-zero coefficient, and 4 is the exponent, so our degree is 4. This one might actually look like a polynomial, but it's not. It does not fit the definition of what a polynomial is. It doesn't fit the general case, because n minus 1, all of the powers are integers. They're non-negative integers. Here, we have a 3 halves. This is a rational number. It's not an integer. So this does not fit the definition of a polynomial. Therefore, it's not a polynomial. Now, since it's not a polynomial, we don't need to list a degree because the degree is only defined within the scope of a polynomial. Try one. Determine if the expression is a polynomial. If it is, determine the degree. And then part A is 3, part B is 10x to the 5th minus 320. I'll leave that to you all. All right, the next topic we're going to cover is addition and subtraction of polynomials. So first thing I need to do is make a note here. Order of operation plays a big role when we add polynomials. So let's go over the order of operations. The order of operations are parentheses. So we resolve parentheses first, then exponents, then multiplication and division, and then addition and subtraction. Recall, x holds the place for a number. When we plug a number in for x, exponents resolve first, then multiplication of the coefficient. So let's do an example here, just as a refresher. Suppose that we had 3x to the 4th, and we said x is equal to 2. Well, then this would look like this, 3 times 2 to the 4th power. Well, 2 to the 4th resolves before multiplication. So we do 2 to the 4th, which would be 16. So then we would have 3 times 16, and then 3 times 16 is 48. Now, if we were to add a number to this 3x to the 4th, it would resolve in the exact same way, and then we would add 48 to something. The addition comes after the multiplication. Since we have multiplication here, 3 times 16, this resolves before any addition. Definition. Like terms are terms with the same variable raised to the same power. Now, in order to add and subtract polynomials, we add and subtract like terms. As an example here, let's say that we had 3x to the 4th plus 2x squared minus 4x plus 5, and we wanted to add this polynomial to another one, x cubed minus 6x squared plus x. Well, here, the like terms are going to be the same variable. That's a given. We have all x's here. We don't have any y's, so all of the variables are the same, namely that we only have one. And we also want to add the terms that have a common exponent. Now, this is because the exponent resolves first. So what we're saying here how you might think about this is I have 3 x to the fourths here. X to the fourth, think of this as an object. I have 3 of this thing, and this thing is x to the fourth. How many do I have over here? Well, I have 0. So I would get 3 x to the fourth. Now I have 1 x to the third here, but I have none over here. So I have an x to the third. I have 2x to the seconds here. So again, think of x squared as an object. I have 2 of this object here, and I have a -6 of this object over here. So how many do I have in total? Well, I have 2 here, and I'm subtracting 6, so I have -4x squareds. Similarly, I have a -4x. Again, think of x as an object. I have 4 of them here, -4 of them here. And I have a single one over here. So I end up with -3x, and then I have my constant term. And that's it. Now, if this was a subtraction, I would have to distribute this subtraction first, and then do the exact same process. Combine the like terms. Now let's talk about multiplying. When we multiply polynomials, we use the distributive property. Right? Let me give you an idea here. Suppose that we have 2 things, a plus b. Now this can be a polynomial where a is a variable and b is a constant, or you might have 2 terms of a polynomial. But when we multiply this by another binomial, or something with 2 things here, then we would have to distribute this whole thing into this sum. So think of this whole thing now as an object. If I think of this as an object, then when I distribute it, I get c times this entire thing plus d times this entire thing. So I would have c, a plus b, plus d, a plus b. Now I distribute again. Now I have a c can distribute into this sum. So c goes here and here. Multiplies to both, and I get ac plus bc plus dA plus dB. Now you can multiply in any order, so if you have it written slightly differently, you could have a CA here instead of an AC, or any of these in reversed order, or in any order, because sums are also added in any order. So I want you to try one now. Multiply the 2 polynomials, x squared plus 1 times x squared minus x plus 1. Next thing we're going to talk about is the special product forms for polynomials. If a and b are real numbers or algebraic expressions, 1, a plus b times a minus b is equal to a squared minus b squared. Now you can actually verify all of these by just doing the distribution. I'm not actually going to verify them though. A plus b quantity squared is equal to a squared plus 2ab plus b squared. 3, a minus b quantity squared is equal to a squared minus 2ab plus b squared. 4, a plus b quantity cubed is a cubed plus 3a squared b plus 3ab squared plus b cubed. And 5, a minus b quantity cubed is equal to a cubed minus 3a squared b plus 3ab squared minus b cubed. Let's do an example here really quick. 2x plus y squared quantity squared. Now, how we use these is through substitution. So match this to one of these and determine what a and b will be. And then we can multiply it out very easily. So here what we're looking at is something plus something squared, quantity squared. So we look for something plus something quantity squared. It happens to be 2. A plus B quantity squared. So my A in this case would be 2x. My B would be y squared. And we know that a plus b squared is equal to a squared plus 2ab plus b squared. So if I pattern match now, if a becomes 2x and b becomes y squared, then I can copy this, paste it here, and replace a with 2x and b with y squared. So I'd have 2x quantity squared plus 2 times 2x times y squared plus y squared quantity squared. So notice that my b is y squared, so b squared will be y squared squared. My b here is y squared, my a is 2x. This 2 just carries over. And then my a squared becomes 2x squared. I want you to try one as well. Use the product formulas to multiply the polynomials. X squared minus 2y times x squared plus 2y. The next thing that I want to talk about is factoring polynomials. Now I want to make a note here. Factoring polynomials undoes distribution. Let me give an example really quickly. Now the basic distribution is undone by common factors. Okay? Suppose that we had, say, 3x plus 12y. What we would do is we would look for a common factor. What numbers or values, what terms can go both into 3x and 12y? That happens to be 3. Now what this means, remember, this 3 is going to distribute into both of these. So I need this number here to be what I would multiply by 3 to get 3x. And that is just x. Then the next number will be whatever number I need to multiply by 3 to get to 12, y, which is 4y. So notice if I distribute this 3 in, it undoes the factoring. So 3 times x is 3x, and 3 times 4y is 12y. B. 12xy plus 4x squared. Okay, what are the common factors here? Well, 4 goes into 12, and 4 goes into 4. So 4 will go both into 12 and 4, so I can pull a 4 out. Similarly, we have an x here, and we have an x squared here. So x will go into 12xy, and x will go into 4x squared. So I can actually pull an x out as well. So now what would I multiply by 4x to give me 12xy? That'll just be 3y. And then what do I multiply by 4x to give me 4x squared? That's just x. So factoring trinomials of the form x squared plus bx plus c. First, I want to make a quick note here. X plus r times x plus s will equal x squared plus r plus s times x plus r times s. So notice here that r and s will multiply and become c, and r and s will add and become b. Now I need to make a very, very strong notion to detail here. This only works when a is equal to 1. So if we had a number other than 1 in front of x squared, this would not work. Okay? You would get a different value. So I want to factor this expression. So my b is 7 and my c is 12. My b is going to end up being r plus s, where r and s are the values that I'm trying to factor this polynomial into. So let's go ahead and this. We need two numbers that multiply to 12 because r and s will become c. So we need two numbers that multiply to 12, r and s, will multiply to 12 in this case, and add to my b, which is 7. So r times s and r plus s. R times s is equal to 12, r plus s is equal to 7. All right, so figure out two numbers that multiply to 12 and add to 7. You should come up with 3 and 4. This polynomial will then factor into x plus 3 times x plus 4. Now again, this works only when your a is equal to 1. This quick process. There's a longer process when a is not equal to 1. Let's go ahead and discuss that next. So now let's look at factoring ax squared plus bx plus c. And do an example here. Now, trust me on this one a little bit because I'm not going to go through the process on how we find this, how we know this to be true. So we're going to multiply to a times c and add to b. So we're still looking for two numbers that add to b, but now we're looking for two numbers that those two numbers also have to multiply to a times c. Now our a is 2. Our c is negative 4. So 2 times negative 4 is negative 8. And our b is 7. So we're still adding up to 7. So I need two numbers that multiply to negative 8 and add to 7. 8 and negative 1 will work in this case. 8 times negative 1 is negative 8. 8 plus negative 1 is positive 7. Right, now there's an intermediate step here that we need to do when we have our a is equal to something other than 1. And our intermediate step is to break up our b term. So notice here, if I combine like terms in the line that I just wrote, I would get back to the original expression. 8x plus a negative x gives me 7x. Everything else remains unchanged. So I have not done anything to change the value of this expression. I've only changed the form. Now what I'm going to do is I'm going to group the first two terms and the last two. Now, I need to stress this. You should have a plus here. So if you have a subtraction, rewrite it as a plus a negative number, like I did. So notice that I could write this as 8x minus x. Instead, I write it as plus a negative x, because you want a plus in between these two when you group them, these two these two binomials. Then we do what we did in, not the previous example, but the one prior, where we look for numbers and values. We look for terms that we can factor out that are common to both terms in the binomial. So here, a 2 is common because I can factor a 2 out of 2 and I can factor a 2 out of 8. And an x is common because there's an x squared here and an x here. So I can pull a 2x out. And then what's left is x here and 4 here. Notice that this is x times 2x gives me 2x squared. 4 times 2x gives me 8x. Now, I know I've been doing it in a way where you look at this number and multiply it by 2x to get to this value. You can also take this value and divide by 2x to get this value. Or 8x divided by 2x gives me 4. Either way works. They're both the same exact process. It's just a little bit different. It's a different steps. It's different steps, but it will resolve to the same thing. Now I can factor out whatever I can here. Now, on the second one, you have to be a little bit more careful. You want your finished product to match the x plus 4 in this case. So whatever I get here, I would like this binomial to match whatever I get here. Now I have a negative x minus 4. So if I factor out a negative, then I would be left with x plus 4. So I'm going to factor out a negative 1, and I'm left with x plus 4. And it's key that x plus 4 matches x plus 4 here, because it's required in our next step. The next step would be to look at these and factor that piece out. Because if we think of this entire thing as a single term, and this entire thing as a single term, then they have a common factor, namely the x plus 4. If you think of this as an object, you can see that it's common in both terms. So I'm going to factor that piece out now, x plus 4, and see what's left here. If I factor out the x plus 4, then what remains is just the 2x. If I factor out the x plus 4 in here, this term, what remains is the minus 1. And then you're done. This is the expression. All right, let's do another example, because we factor a lot in this class, and we really need to understand this thoroughly. Let's say that we have something like this. I would encourage you to pause the video here and try to factor it yourself. Maybe go back and look at the previous example and follow the same steps. We're going to multiply to a times c. A times c is negative 36. And we're going to add to negative 5. What this comes out to is negative 9 and 4. Just to double check, negative 9 times 4 is negative 36. Negative 9 plus 4 is negative 5. It needs to satisfy both conditions. Next step is to break up our b term. 6x squared minus 9x plus 4x minus 6. So again, if we combine like terms in the line that we just found, we would get back to what we had earlier. So I've not changed the value of the expression, I've only changed how it looks. So now we look at what we can factor out of these two. Let me group them just to be thorough. What can I factor? What's common between 6x squared and negative 9x? Well, clearly we have an x, but also a 3. 3 goes into 6 and 3 goes into 9. So 6x squared divided by 3x will give me 2x. And negative 9x divided by 3x will give me negative 3. We do a similar thing here, where we look for anything that is common between the two terms. And in this case, the only thing that's common is 2. So I can factor a 2 out of 4x and a 2 out of negative 6. 4x divided by 2 is 2x. And negative 6 divided by 2 is negative 3. Now notice our 2x minus 3 matches our 2x minus 3. So again, what you want to do is you want to think of this as an object that is contained in two terms, this term and this term. So I'm going to factor that object out because it's common between the two. So I can factor it out. I get 2x minus 3 times whatever's left here, which would be 3x, and plus whatever's left here, which is just 2. So 2x minus 3 times 3x plus 2 will give me this. I want you to go ahead and try a couple here. Now, again, I need to make a note. I need to emphasize this. We factor a lot in this class. You will factor a lot in the next class. You will factor polynomials for the rest of your mathematical career. Understanding this concept is very important. So I urge you to really work on these problems, to practice them. Factor the following. 2x squared plus 5x plus 3. And b, 4x squared plus 8x minus 5. The next thing we're going to talk about is special factoring formulas. So if you remember the special multiplication formulas that we had earlier, if we look at the reverse of these three, then we'll get three properties for factoring, the first three properties. Namely that a squared minus b squared factors into a plus b times a minus b. Now this one has a special name. This one's called a difference of square. And because it has its special name, you should definitely remember how to do this one. 2 a squared plus 2ab plus b squared is equal to a plus b quantity squared. And 3 a squared minus 2ab plus b squared is equal to a minus b squared. Now, as I said, these three come from these first three rules when we multiply stuff out. We multiply out these binomials. We're just starting with this side and going to this side instead. Starting on the right and going to the left. But there are two new ones. For a cubed minus b cubed, this one's called a difference of cubes. A lot of people forget about this one. It comes up enough that you should at least know where it is to look for it. Like know where it is in your book. But remembering it is actually not as important. I'll show you a way to remember it in a second though. And then we have a cubed plus b cubed. This is a sum of cubes, which is a plus b, a squared minus ab plus b squared. So if you want to remember these, and you want an easier way to remember them because they look awfully similar, a cubed minus b cubed will be a minus b. So this sign is the same as this sign for both of these. And then the sign changes for the next sign. The next sum, the sign changes. So if you had a subtraction here, you have an addition here. If you had an addition, you have a subtraction. And remember, this sign matches the sign here. So if you have a cubed minus b cubed, then it's a minus b. If you have a cubed plus b cubed, you have a plus b. The sign changes, and the last sign is always plus. So if you wanted a way to remember it, that's a way to remember it. Let's do a couple examples here. So factor these. A 4x squared minus 9. Now, this one is a difference of squares. 4x squared is the same thing as 2x quantity squared. 9 is the same as 3 squared. So this is actually 2x squared minus 3 squared. So factoring this, my a is 2x and my b is 3. So I should have a plus b will become 2x plus 3 and then 2x minus 3. This one in particular comes up a lot. The difference of squares comes up a lot. So definitely know that one. X squared plus 8x plus 16. Now, very similar, this is the actual x squared plus, if I rewrite this as 2 times 4x, 2 times 4 times x, and then the last part as 4 squared, then you might be able to see that my a is x, my a is x here, my b is 4, and my b is 4 here. So b is 4 and a is x. This would become x plus 4 quantity squared on the other side of that equation. I want you to try one. I want you to use the forms to factor these. x cubed minus 8 and 8x cubed minus 27y to the 6th. Now the second one is very challenging. This is a challenging problem. For both of these, I would suggest that you match up what your a is, figure out what your a and your b are, and then move from there. And the second one should actually be 8x cubed plus 27y to the 6th, not minus. Now I'm going to factor a few special cases, some weird anomalies that happen sometimes when we factor. So first, when we have rational exponents, it doesn't necessarily mean that we can't factor it. It just makes it a little bit harder. So if we have x to the negative 3 halves plus 2x to the negative 1 half plus x to the 1 half, what you want to do is you want to get rid of these negative exponents if possible. And here we can actually do that. What I'm going to do is I'm going to factor out the most negative using the most negative power. So x to the most negative power. X to the negative 3 halves. Okay. Well, what does that mean? Well, remember that whatever goes here multiplied by this gives me this value. In this case, it's obviously 1, but you can also look at it as this term divided by what we're factoring out gives me the corresponding term in the polynomial. So here, we look at it as 2x to the negative 1 half, and we divide by x to the negative 3 halves. Now remember, when you divide by something with the same base and different exponents, you subtract the exponents. So this will look like, if I pull this 2 off, this will be the same thing as this. X to the negative 1 half divided by x to the negative 3 halves. So when we divide these, remember you subtract. So this becomes 2x to the negative 1 half minus a negative 3 halves, which is the same thing as plus 3 halves. So we end up with 2x to the positive 1, or 2 halves, or 1 in this case. So we end up with just plus 2x here. And we do a similar thing here, where we have x to the 1 half divided by x to the negative 3 halves. And remember, you subtract again. So 1 half minus a negative 3 halves gives me 4 halves, or x squared. 4 halves reduces to 2, so we have a power of 2. Then I can factor this, and this factors into x to the negative 3 halves times x plus 1 quantity squared, if we just use the formulas. The last part of this section is going to talk about factoring by grouping. Now, factoring by grouping doesn't always work. I want to make that note. I want to make that very clear. Factoring by grouping doesn't always work, but it is worth a shot. So something that we can factor by grouping will look like this. X cubed minus 4x squared plus x minus 4. Up to this point, we've only factored polynomials that have degree 2 and less. That's all we've ever done. When we have a polynomial with a degree 3, it becomes a little trickier, unless it has a common x and it can reduce very easily down to an x squared. But in this case, not everything has a common x, so we can't factor that out. So what we do is we group the first two and we group the last two, and we see what we can factor out. And in this first one, we can actually factor out an x squared. We have a common x squared here. And in the second one, it already matches our x minus 4 upon factoring an x squared out. So all I'm going to do is factor a 1 out. Factoring out a 1 doesn't change the problem, again, because the 1 is the multiplicative identity, meaning dividing by 1 also doesn't change anything. So now I can factor out my x minus 4 because it's common in both terms. And again, think of this as an object. and it's common to both terms, so I can factor that out. And what's left is x squared plus 1. Now, x squared plus 1 does not factor. It's just, it's a sum of two squares, and it just doesn't work. We can't factor that, at least not yet. When you get into the complex field, then you can factor it. But because we're only dealing with real numbers right now, we cannot factor this. So this will be the end of the problem. This is the lowest we can go. I want you to try one now. Factor this polynomial by grouping, just like the previous example. All right, that'll be it for this section. I will see you all in the next lecture.